The hydrohalogenation of alkynes is going to be the topic of this lesson, and we'll find out it's very similar to the hydrohalogenation of alkenes we learned about in the last chapter, but one big key difference that alkynes have 2 pi bonds, and so it will have the potential to happen either once or twice, depending on how many equivalents of the reagent we choose to use. All right, so we're going to start off with a look back at our hydrohalogenation of an alkene, and this could work with either HCl, HBr, or HI, so I'm using HBr specifically. And you guys might recall that in step 1 we actually form a carbocation. We add H to the less substituted side, leaving us with the more substituted, more stable carbocation, and then bromide would come attack that carbocation, so leading you to net result Markovnikov addition. H on the less substituted side, bromine on the more substituted side. Now with alkynes, we'll find out that we have the option to do this either once or twice, depending on if we add 1 equivalent or 2. Cool, it's still going to be Markovnikov addition, although the mechanism's a little more nebulous when it comes to alkynes here. So in this case, if we got a terminal alkyne, if you look at this lovely terminal alkyne, the left side is more substituted than the right-hand side. And I say that to contrast that with an internal alkyne. And internal alkyne, neither one of these carbons is more substituted than another. So, and a lot of students don't realize that this makes a difference. Like if I have an alkyne here, and then if I have this one here, and I just keep going and going and going, well, it's still an internal alkyne. This is not actually at the end of the chain, and both of these carbons are still equally substituted. It doesn't matter how long the chain is. Notice if you cover up those pi bonds, you'd realize that those are both analogous to being secondary carbons. One is not more substituted than the other. So if neither one is more substituted than another, then Markovnikov and anti-Markovnikov wouldn't really mean anything for an internal alkyne. It could just go either way. And so from here on out, I will work one example with an internal alkyne, but from here on out, I'll probably just be using terminal alkynes for a lot of these reactions. That way we can actually see the difference between Markovnikov and anti-Markovnikov. And so in this first example, it turns out we can add 1 equivalent of, say, HBr or HCl or HI, and 1 equivalent is going to add Markovnikov and lead us here. Now, the mechanism for this is probably one you're not on the hook for, because we're not entirely sure of the mechanism, it turns out here. So it turns out, the likelihood of it going through a similar carbocation-like mechanism is not the most likely thing in the world, because a carbocation on a carbon that's part of an alkene like this is a really unstable alkene. I'm sorry, a really unstable carbocation, less stable than probably like a primary carbocation, which typically isn't, stable enough to form either. And so the likelihood of it going through this kind of an intermediate is pretty unlikely. So we also have some other reason to think that, the way it forms is totally through a second-order process, not a first-order process, which leads us away from that kind of a mechanism as well. But needless to say, we don't entirely know the mechanism, and so sometimes professors will give you a simplified version of a mechanism that maybe is plausible. Sometimes it turns out we actually think there might be competing mechanisms going on, more than one. But often, most of you are just going to get off the hook from having to know any sort of mechanism for this reaction. Now, we've done it once, we did it Markovnikov. It turns out you can also add a second equivalent, and it will go Markovnikov once again. And so typically you got one of 2 ways to go with this. You're either adding 1 equivalent and stopping an alkene, or you're adding 2 equivalents from the get-go or excess from the get-go and going all the way to the alkane. We added 2 hydrogens to the less substituted side, 2 bromines to the more substituted side, 2 addition reactions across that alkene. All right, had we done this, let's say, with an internal alkyne, let's just say we cover this for 1 equivalent of HBr. Well, in this case, then, we're going to add, an H and a Br across this alkene, but neither side is more substituted. So in one case, maybe I did it like this. And then in another case, maybe I add the bromine on this side, the hydrogen on this side, just do it the opposite way, because Markovnikov and anti-Markovnikov don't mean anything. Also, E and Z don't really mean anything, and I'm only showing one of the 2 stereoisomers, and I could get the opposite as well. So, but from here on out, the key is that, for an internal alkyne, just know you could do it both ways, and you can get E and Z and all that stuff. But from here on out, I'm not really going to talk about internal alkynes for most of these reactions for this reason. But you should realize that in principle, when it's internal, Markovnikov and anti-Markovnikov don't mean a thing. Okay. We also taught you in the alkene chapter that if you use HBr specifically, that doesn't work for HCl and HI, but with peroxide, ROOR is our generic formula for an organic peroxide, that it goes anti-Markovnikov. It adds the H to the more substituted side and the bromine to the less substituted side, and the same thing will still apply to alkynes. And once again, we'll go with that terminal alkyne, so we can see the difference and see that anti-Markovnikov means something. And so we'll go one equivalent of HBr with peroxide, and it goes anti-Markovnikov. And the truth is, again, there's no stereoselectivity here, although trans, or I should say E, is more stable than Z. But we have the option of adding a second equivalent. And it's still going to go anti-Markovnikov. Cool. So net result by adding excess or two equivalents is that you get two bromines on the less substituted carbon and two hydrogens on the more substituted carbon. Cool. But once again, just like with regular hydrohalogenation, with peroxide and HBr, you have the chance of doing one equivalent and getting an alkene, or two equivalents and going all the way to an alkane. If you have found this lesson helpful, consider giving me a like and a share. A couple of the most helpful things you can do to support the channel. If you're looking for the study guides or practice problems, check out my premium course on chadsprep.com.